We know what we mean by a function of a random variable, and we also know that we can define several random variables on the same experiment. So a natural step would be to define a function of several random variables. Let's begin by illustrating this with an example. I have an experiment. My sample space is A, B, C. To make it simple, each outcome is equally likely. My first random variable is called X, and it's mapping A to 1, B to 2, and C to 3. My second random variable is Y. It maps A to -1, B to 0, and C to 1. And finally, I have a function of two variables. So it maps from R2 to R. And in this example, it's a very simple function. G of X and Y is simply the product of X and Y. So based on this, based on two random variables and a function from R2 to R, I can define a new third random variable. I'm going to call that Z, and it's going to be G of X and Y. So what random variable is Z? To figure that out, we simply go through all possible outcomes. Beginning with A, X will map that to 1 and Y will map it to -1. So our new random variable Z will map A to 1 times -1 because we have defined the function G as the product of X and Y. So Z will map A to -1. In the same way, it'll map B to 2 times 0, 0, and it will map C to 3 times 1, which is 3. We see that the PMF of Z is simply equal to, well, it can take 3 values. It can take value -1, 0, and 3. A is mapped to -1, so probability of that is 1/3, 1/3, 1/3, and then of course 0 otherwise. So let's just put Z equal to here. So let's have a look at this from a more general perspective. This is then my starting point. I have an experiment. I have a sample space S. I have defined events. I have a probability measure P that assigns a probability to each event. I have defined two random variables. I call them X and Y. And I also have a function G which maps from R2 to R. That is, it's a function of two variables. With this, I can create a third random variable Z, which is G of X and Y. Here's a picture of how Z is defined, illustrating that Z is simply a composition of the functions G, X, and Y. Here's my sample space. Let's just name one of the possible outcome omega. Omega is mapped to a real number by X as well as by Y. So I can do the X mapping along this axis. In the same way, the Y random variable will map omega onto the real line. But if I put the Y axis vertically, I can illustrate the combined mapping X and Y of omega. So if X maps omega here and Y maps omega here, then X comma Y will map omega to this point in R2. So this is my X and Y mapping of omega. So think about it like this. X and Y together will map every possible outcome to a point in the Cartesian coordinate system. Well, the Cartesian coordinate system is precisely the domain for the G function. So I use that as my domain and I map this point using the G function onto the real line, and we call this Z. So this point X comma Y is mapped onto the real line. Z is equal to G of X comma Y. Now this happens for every possible outcome in S. So another point here is mapped to another point perhaps here, which is then mapped by the G function to another point perhaps here. So I can simply create the composition and go straight from omega to the Z value, and this is my Z random variable. it will map every outcome in S to a real number along the z-axis. So we've done this illustration using just 2 random variables, but we can do this with an arbitrary number of random variables. If I have 3 random variables, then they together will map every outcome to a point in R3. And if I have a function g whose domain is R3, that is, it's a function of 3 variables, then I can create a 4th one. So the general idea is that if I have n random variables named x1 through xn, each of them is a function from S to R. Combined, they are a function from S to Rn. That's the domain of a function g. It takes a point in Rn and maps it to R. So I can combine these n random variables and the function g, create the composition z as g of x1 through xn, and that will then be a new random variable. It will map every outcome in S to a real number.